Hi, my name is Corinna Wester, and this is my video for Lab 5, Falling Magnet in a Solenoid. So for our introduction, in today's lab, we're going to be looking at the skills and formulas that we're going to be using. So the first one we use in this lab is Faraday's Law, and we have a falling magnet that creates a magnetic field that in turn creates an induced current in an aluminum tube. And we're also going to be looking at the interaction of forces. We're going to observe and calculate the results of interactions between gravity, magnetic field, induced current, and EMF. And we're also going to use VPython to model and compare calculated and observed results. So our measurements and method. As you can see on the right loop, we hold our aluminum tube upright, and we're going to hold our bar magnet above the open end of tube. We're going to drop the magnet into the aluminum tube and observe and time the magnet as it drops through the tube. Now the measurements for my tube, the inner radius was about 1.15 centimeters. The outer radius from the center to the edge of the aluminum was 2.225 centimeters. So my thickness of aluminum was 1.075 centimeters, and the length of my tube was 30.6 centimeters. After repeating this experiment several times, the average time of my falling magnet was about 2.27 seconds. So here are screenshot captures of the running of my code. Now what this code did was basically it took small dy segments, so basically little slices of ring all the way down the tube, and summed up the forces from the dipole moment so the magnetic field of the magnet and the induced electric current and the induced electric curly E field of the tube, and sum them all up together. So basically performing an integral. As you can see on the left is just the magnet falling through the tube, and you can see that the red and blue that are simulating where the E field and the EMF are. On the right, you can see the velocity versus time graph, and you can see right when the magnet is let go, it shows a steep decrease in velocity. But then as it hits the tube, the velocity levels off, which makes sense because we know that the induced current should go against the force of gravity. So some interpretations. The intensity of the coloring on the tube indicates the magnitude of currents, red and blue indicating currents in opposite directions. So how do we know which color corresponds to which? Well, we know that the induced current goes in the direction of negative d flux dt. So by the right-hand rule, the induced current in our tube should be in the counterclockwise direction of the tube. So what would happen to the dynamics of the system if we were to flip the magnet around? There should be no difference if we were to flip the magnet. The induced current would go in the opposite direction to oppose the change in flux, no matter what direction the magnet was dropped in, and therefore no matter what direction the mu of the magnet was pointing. So how does the total time in the tube of my real-world system compare to that of the computational system, and why might the computational system be more accurate? My observed time was 2.27 seconds, and the computational time was 2.51 seconds. So the computational system might be a little bit more accurate. There's no human error, smaller segments, more accurate summation as the magnet falls versus, the real-world scenario. However, the mu of our magnet could be slightly off or something like that in the computational system. So you would have to use another computational system to get that mu value closer to more accurate. And what does the shape of the velocity versus time plot tell us about the forces acting on the bar magnet? So we know that constant or near constant velocity versus time means that the net forces on the bar magnet should be equal to 0. So conclusions. What if the resistivity of the conductor was reduced to as close as possible to 0, and how would that change the dynamics of our magnet? As resistivity would approach 0, the resistance of the tube would get larger, and the ring current would get smaller and approach 0. This would decrease the magnetic force. And what if rings or holes or slots were cut into the tube? How would this affect the ring currents in our model? If holes were cut into the tube, it would slow it down. It would still slow it down as it went through the tube, but the field would no longer be constant as it would with a solid tube, so the magnet would fall faster, but still not as fast as a normal gravity speed. So in conclusion, this lab modeled Faraday's law, which says that the EMF is going to be directly proportional to the change in flux, and also Lenz's law, which shows that EMF will produce a current that will oppose the change in flux.